All right, guys, welcome to this page of the notes. And what I've got for you here is you'll recognize this formula, right? Except the difference here is now we have 1 minus r instead of 1 plus r. Previously, on a previous page of these notes, we did an exponential growth model where we had 1 plus r. Well, now we're dealing with exponential decay, and so it's going to be 1 minus r. Everything means the exact same thing it meant in the previous formula. The lowercase a will be the initial amount. AT will be the final amount. Remember, I like to use capital A and A naught instead. In fact, here, let me write it for you. I prefer to use A is equal to A naught, 1 minus R, raised to the t power. R is still going to be the rate. It must be a decimal. You cannot use a percentage in the formula. You won't get the right answer. And it's an exponential model because t is a variable and we're raised to the power of t. This quantity is raised to the t power. Now, we use exponential decay models, again, to model all sorts of, a mathematical model for all kinds of natural phenomena. I actually give you a couple of examples here. We can do things like the half-life in chemistry or even carbon-14 dating, exponential decay models. We can do things like population decreases due to overhunting, right? And that's just to name a couple of examples, right? These exponential models can be used to model all sorts of natural phenomena. And I think I mentioned earlier in section 8 of this chapter, we'll take a look at quite a few example problems of sort of real world situations, word problems, where we use exponential functions to model that particular situation or natural phenomenon. But here's the one I've got for you in this case. What I tell you is that the average cup of coffee contains 35 milligrams of caffeine, and the average teenager can metabolize or eliminate 12.5% of the caffeine they consume per hour. What I want to know is I'd like you to estimate the amount of caffeine still in your system 3 hours after consuming a cup of coffee. Right? How much caffeine is still left after 3 hours after you drink that cup of coffee. So let's go ahead and take a look and see what this is gonna turn out looking like. All right, I got my formula right there. Let's go ahead and go through, highlight the stuff that's really important. I have a percentage. That's obviously going to be my rate, but I'll have to convert it to a decimal. I start with 35 milligrams of caffeine. That's what the average cup of coffee has, so that'll be my A naught, my initial amount, about 35 milligrams of caffeine. I want to know how much is left over. That's the final amount. How much caffeine is still left in your system 3 hours after you consume that first cup of coffee. So 3 is going to be our T. Let's go ahead and start plugging stuff in. A is what we're solving for. We're looking for that final amount of caffeine. How many milligrams are still left in your system? The initial amount of caffeine is 35 milligrams. I'm going to have 1 minus. I have to convert 12.5 to a decimal. You either divide 12.5 by 100 or just simply move the decimal point 2 spots to the left. So 0.125. And T is 3 hours. 3 hours after you consume that first cup of coffee. Please be careful of the order of operations here. Don't fat finger something on your calculator. 1 minus 0.125. Take that, raise it to the third power, and then multiply by 35. If you do all of that, actually here I got a calculator right here. Let's see what I come up with. Raise to the third power, multiply by 35. I get 23.4 milligrams of caffeine. All right, so you started, you drank a cup of coffee, and you had 35 milligrams of caffeine in your system thanks to the average cup of coffee. 3 hours after drinking that cup of coffee, actually 3 hours, about the time you feel like you're ready for your second cup, you still have 23.4 milligrams of caffeine in your system that is unmetabolized. The point here is this: please be very, very careful of the cups of coffee and the Mountain Dew. It's got a lot of caffeine in it. It takes you a while to metabolize all of that stuff. It certainly can make it difficult to sleep or get a good night's rest. And we know how much teenagers need to get their sleep. Certainly affects the way that you perform in class and all that stuff. So just be real careful when dealing with beverages that have a high amount of caffeine in them. 12.5% seems like a pretty good rate at which to metabolize caffeine, but as you can see here from the problem, it's actually probably a little bit slower than you would think. So you want to be real careful when drinking those beverages that have a lot of caffeine in them, especially if you're looking to get a good night's rest or sleep before a test or something like that. Just watch out for those beverages high in caffeine. So anyway, this again is a great example problem of an exponential decay model. You will see a lot more. You'll see this formula again when we get to section 8 here in chapter 7. That takes care of this set of notes for chapter 7, section 1. Thanks so much for joining me. I really had a great time graphing exponential functions with you. I can't wait to see you next time. Bye.